Hey folks, my name's Nathan Johnston, and welcome to Lecture 25 of Advanced Linear Algebra. This week is really exciting for this course because up until now, what we've been doing is we've been developing all sorts of tools, but we haven't actually done that many things with them. Well, this week, we're going to do lots of things with them. In particular, we're going to develop 4 really big monster theorems this week. So it's going to be big theorem, then big theorem, then big theorem, then big theorem, all using the tools that we've developed so far. So starting with this lecture, where we're going to look at something called Schur Triangularization. Okay, this is our big theorem for this class. And what it is it answers a sort of matrix decomposition question that we left dangling at the end of the previous course. So remember, at the end of the previous course, we looked at something called diagonalization. And what it was, well, it said that if you have a square matrix, then sometimes you can find a diagonal matrix D and an invertible matrix P such that you can write A equals PDP inverse. And that's only sometimes. The cases where you can do this are exactly the cases when you can find a basis of Fn consisting of the eigenvectors of A. Okay, so as long as you sort of have enough eigenvectors, you can diagonalize A in this way. But there's some matrices that don't have enough eigenvectors, so you can't do this diagonalization. So this leads naturally to a few questions. Okay, and question number 1 is, well, how close to diagonal can you make a matrix via this sort of what we call a similarity transformation? Okay, so if I change A to P inverse AP, well, how close to diagonal can I make this matrix over here on the right-hand side? Can I make it diagonal? Can I make it equal to this diagonal matrix D up here? Or, well, no, not always, but I mean, how close can I make it to that in general, okay, for arbitrary matrices? Okay, another question that comes up now that we understand what unitary matrices are is, well, okay, what if we change out this matrix P for a unitary matrix U? Okay, in other words, what if we, instead of talking about similarity transformations, what if we talk about unitary similarity transformations? And the motivation behind this question is, remember, we think of unitary matrices as sort of the nicest invertible matrices, sort of invertible matrices, but a little bit more rigid than that. They don't also stretch and scale things, they just rotate things around. Okay, so how nice can we make a matrix look under a unitary similarity transformation? And that's actually the question that we're going to start off with. That's the question that Schur triangularization is going to answer for us. Okay, but we're going to come back and talk about this first question as well as we go through the next few weeks. Okay, so we're going to start looking at these types of questions, and the question that, now we're going to start off with the unitary similarity transformation question. So another way of thinking about this, instead of just thinking about abstractly in terms of matrices, you can think about this in terms of linear transformations too. And if you sort of trace things through how things work with standard matrices, right? Remember, every linear transformation is equivalent to a standard matrix. This question, it's equivalent to how simple can we make the standard matrix of a linear transformation if we only look at orthonormal bases of whatever vector space we're looking at, of whatever vector space that linear transformation is acting on. Okay, this first question, this similarity transformation question, this is asking how simple can we make a standard matrix look if we're allowed to use any basis that we like, whereas the second question with unitary matrices is asking how simple can we make the standard matrix look if we're only allowed to use orthonormal bases, okay, which again, we think of those as like the nicest, most rigid bases out there. Okay. So, yeah, here's the big beast of a theorem for today's class. It's called Schur Triangularization, and what it says is, well, if you've got some square matrix, and actually we need not just a square matrix, but a matrix with complex entries, okay? We're not allowing matrices over arbitrary fields now. They must have complex entries for this theorem to work. Real entries are okay as well, right? Because real numbers are complex numbers, but, you know, it has to be within the set of complex numbers for this to work. All right, then what the theorem says is that, well, then there exists a complex unitary matrix and a complex upper triangular matrix such that, well, there we go, A equals U times T times U star, okay? So in other words, via a unitary similarity transformation, we can make A look upper triangular, right? We can transform A into an upper triangular matrix via unitary similarity transformation. Okay, and let's think about this a little bit before we prove it, okay? I mean, like, we would sort of like to get things all the way to diagonal if we could, right? Because diagonal matrices, those are sort of the simplest matrices that exist. But of course, if we're only looking at unitary similarity transformations, that's not possible because it's not even possible via all similarity transformations, right? If you look at all similarity transformations, you can only bring matrices that have a full set of n linearly independent eigenvectors to a diagonal matrix. So here we're looking at even more specialized similarity transformations, unitary ones. So of course, that's not going to be able to go all the way to diagonal in generality, but you can at least always go to upper triangular, okay? So this is really nice because unlike regular diagonalization, Schur triangularization, it applies to any square complex matrix. So that's going to be really useful for helping us prove theorems as we go through the rest of the course here. All right, so where does Schur triangularization come from? Okay, and actually, why do we need complex numbers for this to work here? All right, so what we're going to do is we're going to prove this theorem by induction, okay, on the size of the matrix. Okay, so for 1-by-1 matrices, this is straightforward. The result doesn't even really say anything because every 1-by-1 matrix already is upper triangular, okay? So if n equals 1, A is 1-by-1, then A is upper triangular, just choose U to be the number 1 on both the left and the right? Then everything just falls out. So it already is upper triangular, so of course it's triangularizable. All right, for the inductive step, what we're going to do is we're going to assume that every n-1 by n-1 matrix can be Schur triangularized. So we're assuming that this theorem up here applies to the dimension n-1, and we're going to try to show that based on that, it must apply to dimension n as well. Okay, so that's how the inductive argument is going to work. All right, so here's how the proof goes. Suppose that you've got some n by n matrix now, and again, we're assuming that smaller matrices can be Schur triangularized. Well, because this is a complex matrix, we know from the fundamental theorem of algebra that A has some eigenvalue and corresponding eigenvector. So let's just call them lambda and v respectively. Okay, the reason that we need complex numbers in the fundamental theorem of algebra, remember, is the way that you find eigenvalues is by looking at the characteristic polynomial and finding a root of it. As long as we're okay with complex roots, then great, we can find a root. Okay, so this eigenvalue lambda, it might be a complex number. This v, it might have complex entries, even if all of the entries of A happen to be real. Okay, now what we're going to do, and actually another thing that I should clarify before we go any further, we only need one eigenvalue and eigenvector. We don't need all of them, okay? So I'm just picking one eigenvalue, doesn't matter which one, okay? Just one eigenvalue arbitrarily and some corresponding eigenvector. All right, and then what I'm going to do is I'm going to construct a unitary matrix out of that eigenvector, okay? So what I'm going to do is I'm going to assume without loss of generality that that eigenvector has been scaled to have norm 1, okay? So I'm actually going to pick a unit eigenvector v, okay? So that's what I mean by unit eigenvector. I mean an eigenvector with length 1. So I just take whatever eigenvector I find and scale it down so that it has length 1. All right, and then what I'm going to do is I'm going to construct a unitary matrix that has that unit eigenvector as its first column. Okay, so that's all that I'm doing here. U, it's just some unitary matrix that happens to have V as its first column. Okay, if you think about one of the many ways that you can define unitary matrices, one of them is, well, it's any matrix whose columns form an orthonormal basis of, well, n-dimensional space, Cn in this case. Okay, so I'm just picking U to be a unitary matrix that has, some orthonormal basis as its columns, and the first member of that orthonormal basis happens to be V. Okay, and you can always do this. You can always find such an orthonormal basis just via the Gram-Schmidt process, right? You just take this vector V, throw it in some set, and then throw in a bunch of other junk to fill it out to a linearly independent set with n vectors, and then you apply Gram-Schmidt to that set, and you'll get an orthonormal basis that starts with V. You throw those as columns into a unitary matrix, and you get a unitary matrix. All right, so just find some unitary that has V as its first column, okay? And then what we're going to do is we're going to compute some weird matrix product. I claim that U, this U that we just computed, it's going to help us get a little bit closer to upper triangular. So what I'm going to do is I'm going to compute U star AU. Okay, and if I do that, okay, I haven't really done anything here. U star is just this matrix, and U is this matrix. Now let's do that block matrix multiplication. Okay, so I'm going to do this product on the right first, and when I do that, the A just goes into both of these guys, and I get an AV and an A big V. Okay, and now I'm going to use the fact that, hey, A times V, well, V is an eigenvector of A, right? That's how we picked V in the first place. That's how we picked this little vector V. Okay, so A times V equals lambda V. That's all I'm doing in the next step, okay, because it's an eigenvalue-eigenvector pair. Okay, and now I've got a product of two block matrices, so let's just do that product. I'm going to get a 2 by 2 block matrix, right? I'm going to get V star times lambda V. Oh, that's this product up here. I'm going to get V star times AV. That's this product up here. And then similarly, big V star times each of these guys gives you the bottom two entries. Okay, so it's just block matrix multiplication. Okay, now that at first it looks like a really big ugly mess, but here's the key insight. Here's the really fancy thing that happens. Okay, if you look at this really carefully, this bottom left entry, V star, big V star times V, that's actually the zero vector. Okay, and the reason for that is, remember where this big V and little v come from, right? Those come from this unitary matrix here, right? Little v is one column of a unitary matrix, and big V contains all the other columns of a unitary matrix, so big V star. Now its rows are all orthogonal to little v, right? So when you do this product, right, the way matrix multiplication works is you're doing a row of v times little v, and then another row of v dotted with little v, and then another row of v dotted with little v, and so on. Each of those products is just the number 0 because all of the rows of v star, they're orthogonal to little v. So this product here is just the zero vector, okay? So the bottom left corner there is just the zero vector. In other words, this leftmost corner of u star AU, this leftmost column of u star AU, well, it only has one non-zero entry. It's got a number up here, right? This is a 1 by 1 block in the top left corner, okay? So it's got some number there. I don't have any control over that, but all of the other entries in this leftmost column, they're all zeros. Okay, so it's a little bit closer to upper triangular. It's got some number and then zeros, and then junk over on the right-hand side in these n-1 columns over here. All right, so it just got us a little bit closer to upper triangular. It didn't get us all the way there, but this is where the inductive step comes in. The inductive step is now useful because, hey, this block down here is n-1 by n-1. And my inductive hypothesis was I can Schur triangularize n-1 by n-1 things, okay? So now I've gotten this whole thing a little bit closer to upper triangular. I just do Schur triangularization down on this block now, and that gets me the rest of the way there, all right? So here's how it works. We notice that, hey, this matrix in the bottom right corner, V star AV, yeah, that's n-1 by n-1. So by the inductive hypothesis, we know that it can be Schur triangularized. In other words, there exists some new unitary matrix that we're going to call U tilde, and some new upper triangular matrix that we're going to call T tilde, such that, yeah, that V star AV equals U tilde, T tilde, U tilde star, okay? So in other words, we can Schur triangularize it. Okay, and what we're going to do is now we're going to combine this Schur triangularization of the smaller matrix and this sort of almost triangularization of the bigger matrix that we have together to get an actual Schur triangularization of the bigger matrix. Okay, in particular, what we're going to do is we're going to see what happens if we compute this product here. Okay, so to remind ourselves, this U comes all the way from back earlier in the theorem, right? That's the same U that we constructed back up here that has little v as its first column and then big V as the rest of its columns. Okay, and then over here on the right, this matrix here, this is a block matrix with the number 1 in the top left 1 by 1 corner, and then a zero vector over in the rest of the first row, and a zero vector down in the rest of the first column, and then this U tilde, which is n-1 by n-1, down in the bottom right corner. Okay, and when I multiply these together, U, remember, was a unitary matrix, and it doesn't take too much to check that this is a unitary matrix, and when you multiply two unitary matrices together, you get a unitary matrix. Okay, so there are a couple of things to check there, a couple details, but this whole thing is a unitary matrix. Okay, and what I'm doing is I'm just doing a unitary similarity transformation on A here, and I'm going to hope that I get something upper triangular. If I do, then the theorem's done. Okay, so let's see how this works. Let's compute this product here. The first thing that I'm going to do is I'm going to sort of multiply by these U's on the inside here, right? When I star this entire bracket here, I'm going to get a U star right next to A on the left, and I've already got a U on the right here. So I've got U star AU sandwiched in the middle of these two matrices on the outside, okay? And U star AU, we already computed that up above, okay? That's exactly this matrix here. This is U star AU. Okay, so I'm just plopping that down in the middle of these 2 by 2 block matrices that I have left over on the outside. Okay, and now to compute the rest of it, I just do block matrix multiplication. It's just like multiplying together 2 by 2 matrices, right? Okay, so let's see what happens. Well, after you go through all of the ugly calculation, it just turns out that, yeah, you do get something upper triangular. And why is that? Well, here we've got something block diagonal. Here we've got something block diagonal. So that when you multiply those types of things together, it's not going to affect the block upper triangular structure. But then the important point is here in the bottom right corner, what happens is you're going to get u tilde star times this thing, and then a u tilde over on the right-hand side there. And what that's going to do is it's going to turn it into t tilde because of this equation here. We're just using this equation in the bottom right corner after we multiply it out. Okay, so that'll get us t tilde, and t tilde is upper triangular, right? It's an n-1 by n-1 upper triangular matrix. So here we've got a 1 by 1 block, here we've got an upper triangular block, here we've got zeros. So the whole thing then is upper triangular, which is what we wanted, okay? That's finally the end of the proof of the Schur triangularization theorem. So yeah, every matrix can be upper triangularized by some n by n complex unitary matrix. Okay, before we proceed to see what other types of things we can do with this theorem, let's make a whole bunch of notes about it to try to get a little bit more comfortable with it. Okay, and the first thing that you really have to remember about this theorem, it's really important, the entries on the diagonal of the triangular matrix in this Schur triangularization, those are the eigenvalues of the matrix A, okay? The reason for this is that, well, the eigenvalues of a triangular matrix are always its diagonal entries, okay? This is something we learned in the previous course, okay? Eigenvalues of a triangular matrix are on the diagonal, okay? And, well, if you trace it through, you're going to find that any matrix, whenever you change a matrix to be a unitary similarity transformation, or even just any similarity transformation, eigenvalues don't change. Okay, so A and any matrix T in a Schur triangularization of A, they must have the same eigenvalues. The reason for that is, well, just look at the characteristic polynomial. Okay, the characteristic polynomial of t, well, that's determinant of t minus lambda I, and I'm just going to sort of rewrite that in a whole bunch of different ways. I'm going to find that it's actually the exact same as the characteristic polynomial of a. Okay, so what I'm going to do is I'm going to say, okay, well, t, I can just swap in this matrix for t here, right? I can just swap in u star au, that's the same thing. Okay, but now I can just sort of pull those u and u star out to the sides here, right? I can pull a u star out to the left and I can pull a u out to the right because, well, when they multiply together with this I in the middle, we also get, you know, just an I again, okay? It doesn't affect anything there, okay? So if you multiply this crap together, you get this junk here, okay? So I can factor out the u star and the u. Okay, and the reason that it's nice to do this is because, remember, the determinant is multiplicative. If you have a product of matrices inside the determinants, well, it's exactly the product of the corresponding determinants, okay? So I can split this up into a product of three determinants, a product of determinant of u star, and then determinant of a minus lambda I, and then determinant of u, okay? And then we're gonna remember that, hey, determinant of u star, well, u star, because u is unitary, that's the exact same as u inverse. Okay, and again, we have a theorem from the previous course that tells us the determinant of u inverse is 1 divided by the determinant of u, right? The determinant of an inverse matrix is just the inverse of the determinant. Okay, so here we've got 1 divided by determinant of u. It's going to cancel with this determinant of u over here on the right-hand side. Okay, so cancel, cancel, and all we're left with is determinant of a minus lambda I from the middle here. Okay, and now we just recognize that, hey, this is exactly the characteristic polynomial of a. Okay, so characteristic polynomial of a is the same as the characteristic polynomial of t, so they have the same eigenvalues, and hey, the eigenvalues of t are exactly its diagonal entries. Okay, so diagonal entries of diagonal entries of the triangular matrix in a Schur triangularization are the eigenvalues of the original matrix. Okay. All of the other entries in a Schur triangularization, though, they're very not unique, okay? So if you look at the off-diagonal entries of your triangular matrix T, yeah, they can vary wildly. For the same matrix, you might have different Schur triangularizations that have very different upper triangular entries in that triangular matrix T. And also, all of the entries in U can vary wildly, okay? They can be all over the place. You can construct different Schur triangularizations of the same matrix where the unitary matrices U in those Schur triangularizations look completely different from each other, okay? And the reason for that, to sort of convince ourselves of that, is, well, let's think about how we compute Schur triangularizations, okay? One way to compute Schur triangularizations, the way that's sort of hinted at by the theorem, but the proof of the theorem that we just went through is, well, you compute an eigenvalue and eigenvector of the n by n matrix that you start with. Okay, it doesn't matter which eigenvalue and eigenvector you choose, just some eigenvalue and eigenvector. So that gives you sort of the first piece of freedom in the construction of the Schur triangularization. Okay, and then the next thing that you do is you do Gram-Schmidt to extend that to an orthonormal basis of n-dimensional space. So in other words, you construct a unitary matrix whose first column is that eigenvector that you just computed. Okay, and again, there's a lot of freedom here. There's a whole boatload of different unitary matrices that have that same first column. So again, there's a lot of freedom there. Okay, and then the next thing that you do is you sort of induct. You go down in dimension. Okay, so we are already taking care of the n by n thing. Now you go down to sort of the n-1 by n-1 bottom right-hand corner. And you do the exact same thing there. You find an eigenvalue and an eigenvector. Doesn't matter which one. You pick your favorite eigenvalue and eigenvector pair. And then you do Gram-Schmidt extended to an orthonormal basis. That gives you an n-1 by n-1 unitary matrix. Okay, and then you keep on doing that over and over and over again, all the way down until when that bottom right corner is 2 by 2. And then you find an eigenvalue and an eigenvector of that 2 by 2 matrix extended to an orthonormal basis, so you get a 2 by 2 unitary, and yada, yada, yada. It's a hideous procedure, but there's a lot of freedom in it, a lot of choices that you can make along the way, so your Schur triangularization can look very different depending on those choices that you made. Okay? But in practice, this is not something you want to do. We do not actually want to compute Schur triangularizations in practice. Think of Schur triangularization as a theoretical tool. It's a very, very useful theoretical tool. It's extremely useful to know that we can Schur triangularize every matrix, but we don't actually want to do it. All right, so to try to convince you that it's a useful theoretical tool, let's see what types of things we can prove really easily now that we have it at our disposal. And the reason that it's a useful theoretical tool is because it applies to every square complex matrix, right? Unlike diagonalization, which you had this weird eigenvector condition that you had to make sure was satisfied. Schur triangularization, it applies to every square complex matrix. So here's sort of an example of how you can do really nice things with it really quickly. Suppose that you've got some square complex matrix and just give names to its eigenvalues, right? Call them lambda 1 up to lambda n. Okay, then two really nice things happen. The first nice thing that happens is the determinant of that matrix is just the product of the eigenvalues. It's lambda 1 times lambda 2 up to times lambda n. Okay, and the trace of that matrix is the sum of the eigenvalues. The trace, remember, that's the sum of the diagonal entries. Well, it turns out it's also the sum of the eigenvalues. It's lambda 1 plus lambda 2 all the way up to plus lambda n. Okay, so you can prove this directly from the definitions, right? You have to do some ugly mucking around with characteristic polynomials and coefficients of characteristic polynomials, but using Schur triangularizations is a lot easier, okay? So let's see how we can prove this theorem really quickly and easily now that we know about Schur triangularizations, okay? So our first step is gonna be, well, let's just take this matrix and Schur triangularize it. So let's write it as U, T, U star, where U is unitary and T is upper triangular. And let's just see what happens. Well, first we're going to recall that the diagonal entries of T are exactly the eigenvalues of A. In other words, the diagonal entries of T are lambda 1, lambda 2, all the way up to lambda n. Okay, and now let's start thinking about determinants. Okay, determinant of A, well, we're writing A in a Schur triangularization. So determinant of A is determinant of UT U star. And now we're going to do a similar trick to what we did earlier in this lecture. We're going to note that, hey, we've got a product of things inside a determinant. I can split it up into a product of determinants. Determinants are multiplicative. And then again, similarly to what we did earlier in this lecture, determinant of U star, that's exactly 1 divided by determinant of U, right? U star is the inverse of U. So those determinants just cancel out and we're just left with determinant of T. And now the nice thing about T is it's upper triangular, and we have a theorem from the previous class that says, hey, the determinant of an upper triangular matrix is just the product of its diagonal entries, okay? Determinant of an upper triangular matrix is the product of its diagonal entries. What are its diagonal entries? Well, they're lambda 1 up to lambda n. They're the eigenvalues of A. So just multiply them together and you get that determinant. Okay, and that's all that there is to it, right? Proved it in basically 2 lines. Okay, we also have this other equality to prove, trace of A equality. Well, let's do that, and the argument's going to be very, very similar. Okay, so let's look at the trace of A. Well, again, we're just going to sub in that Schur triangularization, so A equals UT U star. Okay, and we want to somehow get rid of the U star in there. Okay, and the trick this time is we're going to use cyclic commutativity of the trace, right? Remember, if you've got a product of things inside the trace, you can sort of cyclically commute them around. You can take the last guy and put it on the front, and then you could take the next last guy if you wanted to and put it on the front. So here I'm just going to wrap this U star around, put it on the front. And now I've got a u star times u. Well, u star is the inverse of u, right? It's a unitary matrix, so that's going to cancel out. And I'm just left with a t on the inside here. And then again, what are the diagonal entries of t? Well, they're the eigenvalues of A. They're the lambdas. So the trace of that matrix is the sum of the diagonal entries, and those diagonal entries are the lambdas. And then we're just done, okay? So again, it just falls out in a line or two, okay? Once you can sort of take your matrix and transform it into an upper triangular one, it's a lot easier to work with because we have a lot of really nice results about upper triangular matrices. Okay, so that'll do it for this class. Next class, we're going to look at another really nice thing that you can do with Schur triangularization. Basically, in a sense, the rest of this course is nice things that you can do with Schur triangularization. Okay, so we're going to look at other corollaries, a little bit beefier corollaries in the next couple lectures. So I will see you then.